And finally, the last one, an elevator initially moves downward with a speed of 16 meters per second. The elevator needs to come to rest without causing people in the elevator to experience an upward force greater than 1.4 times their weight. Otherwise, injuries could occur. How much time and how much distance does the elevator require to stop? Time and distance? Wait a second. Those sound like quantities that we studied way back in 2.3 when we were looking at kinematic, those 4 big equations. Well, let's see. Where are we going to start? The hint here is force. So we're going to first find our acceleration. And then once we have that acceleration, assuming it's constant, which there's no reason for it not to be, then we can find distance and time. Remember, those 4 equations are only good if there is a constant acceleration. So to first find acceleration, we have force, so we're going to start with a free body diagram. We know downward force is going to be the weight, or mg, and the upward force is going to be the normal force that the people are experiencing. So we're going down, so our velocity is going down, but we're slowing. So that means our net acceleration needs to be in the opposite direction, or up. So we'll call that the normal force. All right, so now we have a free body diagram. Great. Once we have a free body diagram, we can look to see which one of these is going to win the tug of war. The stuff that makes it go minus the stuff that holds it back will give us our net acceleration. So Fn minus mg equals m times a. And that a is what we're looking for. And it's coincidentally what I have trouble writing for some reason. All right. We know that this can't be more than 1.4 times their weight, the normal force. So that means we are going to use that 1.4 as a multiplier times mg minus mg equals ma. Okay, so we have mass in all 3 terms, so that can go away. All right, so we have 1.4g minus g. Well, isn't that basically 1g? And all of that will, of course, equal a, bringing it down from above. So we can pull out g from each term, and we have 1.4 minus 1 equals a. So a equals 0.4 g. So a equals 4 meters per second squared. Okay. Now that we have acceleration, and it does not appear to be changing, it is staying constant for us, we can take that and find d and t. What did I write up here? K? What the heck? D and t. All right, so finding these kinds of things, the best method will be to guess it. So we know the acceleration equals 4 meters per second. Units left off for space. Downward with a speed of 16, so our initial velocity is 16 meters per second. Elevator needs to come to rest, so our final velocity is going to be 0. What do we need to find? Let's first find that distance, or x, dx, y, whatever you want to call it. I don't care. Let's just agree on x for this. So if we're looking for x, then we have a, v, and x, but no time. So let's use the no time equation. Vf squared equals v naught squared plus 2a delta x. Substituting in, we have the initial velocity of 16 squared, final velocity is 0 squared, plus 2 times a, which is 8 times delta x. Moving over 16 squared is going to be 256. Subtracting out, negative 256 equals 8x. Divide by 8 on each side, and we get x equals 32 meters. Good. Now we need to find time. Let me get a new page here. All right, so now to find time, we now have x. We can even add that into our given information if you like. X equals 32. Let's see here. VF, 0, V naught. So let's use velocity as a function of time. VF equals V naught plus AT. Solving for t, we get VF minus V naught divided by A. So we have t equals negative 16 divided by A, which is 4. Oh, Mr. Scopetis, you forgot your negative. We're slowing down to a stop, so we have a negative acceleration there. So that would be a negative acceleration. I knew that was a mistake. Well, I knew it was a mistake I was going to make. But I also knew that it was a mistake because if I did not have a negative 4 on the bottom, then that would give me a negative time. You can't have negative time. So t equals whatever negative 16 divided by 4 is, seconds. That's it. A lot of work, I know, but good exercise in thinking. Good job.